This is a re-recording of the first 15 minutes of the lecture on Monday, January the 27th. I had some computer issues at the beginning of the lecture, so the lecture started late, and then I forgot to press the record button on the streaming service, so the live stream started late. If you were trying to watch on the live stream, you probably missed the first 10 or 15 minutes of the lecture. So I'm re-recording that now. At the beginning of the lecture, we were asked to show a slide describing what academic consideration is. So I'm just going to play that video now. Okay, so we were then asked to show this slide. In particular, this addresses what happens if you are experiencing COVID symptoms. So you're allowed one 3-day request each semester without any supporting documentation. If you need more than one academic consideration, then those require additional supporting documentation. If you need more information, you should follow this link. That's their new website, their new streamlined website, and you can contact the necessary people during their office hours at these times shown here. Okay, so in this lecture, I'm going to finish up the previous lecture from Friday. So at the end of Friday's lecture, we were talking about how to write a small simulation so that you could calculate the odds. You calculate the odds of seeing a number that you've rolled using 2 dice, right? So how many times? What are the odds of if you roll 2 dice? What are the odds that you roll a 2 or a 3 or a 4, and so on up to 12, right? And the purpose of this is really to get some practice using a list. So now I want to do a second similar simulation. This time, I want to answer the question: if you flip a fair coin n times, how many heads do you expect to see? Or a similar question: how often do you expect to see n over 4 heads, or n over 8 heads, or 0 heads, or n heads, or anything like that? So if you've taken some statistics before, you know that the distribution of the number of heads that you see follows what's called the binomial distribution. If you don't know, if you haven't taken a statistics course before, then you can try to estimate the probabilities by writing a small computer simulation. What I want to do here is essentially fill in this table, right? So this table here, what is the probability that if you flip a coin n times, what is the probability that you see 0 heads, right? What is the probability that you see 1 head? What is the probability that you see 2 heads, and so on, up to n, right? You can kind of guess that if n is fairly large, say 20 or so, that the probability of seeing 0 heads if you flip a coin 20 times is very low, right? Similarly, the probability of seeing 20 heads if you flip a coin 20 times is also very low. And you might guess that the probability of seeing 10 heads if you flip a coin 20 times, the probability is probably relatively high. Okay, now to write this kind of simulation, you can use the following recipe. So what I want to do is I want to represent this column of the table, the probability column, using a list, right? So I'm going to make a list that has n plus uh, n+1 elements in it, right? The first element of the list will correspond to the probability that I see 0 heads, right? And the last element of the list will correspond to the probability that I see n heads, right? So there's a total of n+1 elements in this list, right? So this number of heads here, this is just the index into the list, and this column here will just be the list, right? So I want to make a list, and I want to fill it with n+1 zeros, right? So in other words, I want to fill this column up with zeros. And then basically what I want to do is I want to simulate flipping a coin n times, and I want to do this many times, right? So m is going to be the number of times I simulate flipping the coin n times, right? So I'm going to call this the number of trials of this experiment that I'm going to run. So I'm just going to repeat the following m times, right? I'm going to initialize a count, a variable called count, to 0. And so count is going to represent the number of heads that I've seen after flipping the coin n times, right? And then I'm just going to flip the coin n times, right? So to simulate flipping a fair coin, you can randomly generate true and false values, right? If you see a true value, then we can say that's a head. And if you see a false value, we can say that that's a tail, right? And we can simulate flipping a coin using the random number generator class called random, right? So random has a method called next Boolean that returns a random true or false value, right? So after I flip a coin one time, if it's a head, so in other words, if the random number generator returns true, I just add 1 to the count, right? Because I've seen one extra head in this round of flipping the coin n times. After I flip the coin n times, right, I now have some value for the count, right? So the count is going to be some number between 0 and n inclusive, right? So I now just go into the list, right? Oops, I go into the list, right? And I find the value, right? So suppose the count is 2, right? Then I look at the value that's here, right? And I add 1 to the value that's here, right? So I'm going to count the number of times that I've seen 2 heads, right? I'm going to count the number of times I've seen 0 heads, 1 head, 3 heads, up to n heads, right? Now to get an estimate of the probability, at the end of, after doing this m times, you divide every element in the list by m, and that gives you an estimate of the probability, right? So in Eclipse, I'm just going to show you the simulation in Eclipse now. Okay, so I have a class called CoinFlip, right? Inside the class, it's got a main method, right? So here I want to simulate flipping a coin 10 times, right? And I'm going to do that 1 million times, right? So n is the number of times to flip the coin in one trial, and m is the number of trials that I'm going to perform, right? I then want to make my list, right? So my list of probabilities. So that's called PROB, right? Short for probabilities. And remember that the list probability I, that's the approximate probability of seeing I heads when flipping a coin n times, right? So prob 0, that's the probability of seeing 0 heads when flipping a coin n times. Prob 1 will be the probability of seeing a 1 head when flipping a coin n times, and so on and so on, right? So I start by filling in the list with all zeros, right? And I just use a little loop to do that, right? Notice that I go up to and including n in this case, right? So I start at 0 and go up to and including n because there's n+1 elements in the list, right? Next, I make my random number generator, right? And then I perform the m trials, right? So the m trials of flipping the coin n times, right? I initialize my counter to 0. Now I flip the coin n times, right? The way I flip a coin is by using the random number generator and calling the next Boolean method, right? If I get a true value, then I add 1 to the current count, right? And if I get a false value, I do nothing, right? So when this loop runs n times, I flip the coin n times, right? And I now have a count of how many heads I've seen, right? So I go into the list, right? So I go into the list at index count, right? And I add 1 to the value that's currently in that's currently at index count, right? So prob get count, that's the number of that's the value that's currently in the list at index I or at index count, right? And I add 1 to it because I've just seen one more instance of getting count heads, right? So that's the new number of times that I've seen count heads, and I put that back into the list at index count, right? And so when this loop runs m times, what you end up with is the simulated distribution of the number of times you see any number of heads from 0 up to n, right? So now I want to divide everything by m, right? So I want to divide every element in the list by m, right? And the way you do that is prob get I, right? That's the number of times that you see I heads, right? You'll divide that by m, right? So I'm just taking one element of the, I'm getting one element of the list, dividing that value by m, and then putting it back into the same location, right? So that's what set does, right? Set I sets the element at index I. And then I'm going to, this isn't on the slide, but I'm going to calculate what's called the cumulative probability, right? And this is just as a double check. You'll see what this value comes out when I run what value comes out when I run the method, right? And then I'm going to print out the probability, the list of probabilities, and the cumulative probability, right? Okay, so let's run this. Okay, and when I run it, you get some values that are a little bit hard to understand, right? So this is some small value. It's times 10 to the minus 4, right? That's roughly 1 times 10 to the minus 2, right? That's 0.04. And then we get some other values here. You can see that it peaks roughly in the middle, right? Instead of printing out the probabilities, why don't we just print out the counts, right? So when we run this, okay, now each one of these values is the number of times that I've seen a certain number of heads, right? So that's the number of times I saw 0 heads. That's the number of times we saw 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10 heads, right? So you can see that you do see no heads and all heads occasionally, right? If you do this enough times, right? So if you flip a coin 10 times, sometimes you will see 10 heads or no heads, right? Notice that the cumulative probability is just equal to the number of times that we've, the number of trials that we've, the number of times that we've tried flipping the coin n times, right? The number of trials that we ran. When you divide by m, right? When you divide by the number of trials, that gives you the actual probability. That gives you an estimate of the actual probability, right? So you can see that the probability of rolling all heads is 0.001. So about 1/10 of 1%. You see all heads. Sorry, no heads, and roughly 1/10 of 1% will you see all heads, right? And not surprisingly, 0, 1, 2, 3, 4, 5, right? The most likely number of heads you see is 5, right? Which isn't that surprising, right? On average, you expect to see half, right? Half the time you flip a coin, you expect to see heads, right? So it's not surprising that the middle, or 5, right? If I flip a coin 10 times, the highest likelihood is that I see 5 heads, right? This thing's also, it looks like it's symmetric, right? So it looks like this value is approximately equal to this value, and this value is approximately equal to this value, and so on and so on. So this thing actually looks like a curve, right? So it actually looks like a bell curve shape. And as the value of n increases, it gets closer and closer to resembling the actual bell curve or normal distribution, right? So if I run this, if I try to flip the coin 20 times, right, you see that we never see no heads. We see one head very, 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 very rarely, and the same thing on the other side, right? We never see 20 heads, and we only very rarely see 19 heads, and so on and so on, right? Okay, and so that's how you would write the coin flipping simulation. All right, so I basically covered almost everything that I want to talk about for lists. So lists have the three main methods in lists are add, so you add something to a list, get, which lets you get an element at an index in the list, and set, which lets you set an element at an index in a list. Some other methods are useful as well. Contains tells you if an element is in the list. Remove lets you remove an element from a list. And a method like add all lets you add all the elements from another list or set into a list. Okay, now I want to start talking about sets. So a set is a collection of unique elements, right? So in other words, it's a collection where no two elements are equal to one another, right? And you can think of lots of examples of sets in real life, right? So for example, the provinces of Canada form a set, right? The states of the United States would form a set. Student numbers form a set, right? Every student is supposed to have a unique student number. Social security, social insurance numbers in Canada, are supposed to be unique, right? Driver's license numbers should be unique, and so on and so forth. So there's lots of things that actually form sets in real life. For programming purposes, the times you would use a set include, or applications where you would use a set include membership testing. So that's when you want to ask the question, is this element a member of this set, right? If you have a list or an array of elements and you want to remove the duplicates from that list or array, you can use a set. So you just put all the elements into the set, right? Because a set only allows unique elements, that will remove any duplicates, right? And sets also are also model the mathematical notion of a set. So you can perform operations such as the set intersection or set union or set difference. Now in Java, you need to know how to use a set in order to effectively use a map, right? And a map in Java is similar to a Python dictionary. Sets have no indexing, right? So it's just a collection of elements, right? So there's no indexing, which means there's no element 0, there's no element 1, there's no element 2, and so on and so forth. Because there's no indexing, you can't do any slicing using an index or indexes with a set, right? And that's true in Python as well. Now in Java, there are some types of sets that support returning a subset of a set. So in other words, there are sets that support a kind of slice of the set.
Main kinds of sets in Java. There's something called the hash set, right, which is most similar to a Python set, but since you guys have never used one, that's not going to help you, right? Then there's something called a tree set, which is a set where the elements are sorted, right? So the set keeps the elements in sorted order. Right? Now, one big difference between Java sets compared to Python sets, again, so containers in Java, they all hold elements of the same type, right? Almost always hold elements of the same type, right? Unlike Python, where you can shove whatever you want into a collection, right? Again, the type is specified inside the less than and greater than sign when you declare the set, right? So just like a list, you have to say what is the element type that's going to go into this set. So here's how you create a set in Java, right? So you're using the new operator because we need to make an object, right? I'm going to make a hash set in this case, right? And it's a hash set that can store a bunch of strings, right? So I'm making a unique collection of strings in this case. Right. Now, for a modern version of Java, you don't need that. You don't need the element type on the constructor call. Right? You still need it on the left-hand side when you declare the variable, but you don't need it on the constructor call. Right? So the compiler can figure out that you want to make a set of strings in this case, right? Because on the left-hand side you said that t is a variable that can hold a set of strings. Okay, like lists, there are no sets of primitive elements, right? So again, because of the way that Java's generic type mechanism was created, you can't make a set of int, for example, or a set of double, or a set of Boolean, right? You have to use a wrapper class, just like we did with lists, right? So for example, if you want a hash set of int, you have to use a hash set of big I integer instead, right? Okay. Now, since you haven't used these in Python, this side's probably not terribly useful for you. So I just go through them one at a time. Right? If you want to make an empty set in Python, you use t equals set around brackets, or you use t equals brace, right? The empty braces. In Java, you have to use the new operator to make any object, right? So it's always variable type, variable name, equals new, and then constructor call. If you want to check if a set is empty in Python, you just write if t, right? In Java, you call the isEmpty method. Right? The size of a set is given by the len function in Python. Right? But in Java, it's the size method. Right? Now, adding stuff to a set is the same as adding stuff. In Python and Java, it's the same. You use the add method. So if you try to add a duplicate element to a set, then the Java version of add returns false. Right? So it doesn't add the element to the set, right? Because there's already one there, and sets are supposed to be collections of unique elements. If you wanted to check if a thing is in the set, in Python you use in Java you use contains. Right? To remove something, it's remove on both sides. Right? Remove in Java will return true if the element is removed. Right? So if the element is in the set, it will be removed and true will be returned. If the element is not in the set, then nothing's removed from the set and false is returned. Finally, if you want to copy a set, then in Python you use the copy method. In Java, you just make a new object and you call the constructor and pass in the set that you want to copy. Right? So here I make a new hash set called u, and I pass into the constructor the set I want to copy. Right? So that's an example of a copy constructor call in Java. Okay, now when you make a set, normally you choose between two different kinds, but in Java there are many different kinds. Right? Most of the other ones have very specialized uses. So the two general purpose ones are hash set and tree set. Okay? So hash set is the one that you normally pick, right? Because it's extremely fast add, remove, and contains. Right? So you can add something very quickly to the set, you can remove something very quickly from the set, and you can ask the set, hey, do you contain this particular element? Right? And for a hash set, they all have O1 expected complexity, right? So constant time complexity. Right? Now, the odd thing about hash set is if you put a bunch of elements into the set, and then you loop over the elements, the way that you loop over the elements is normally different than the order in which you put things in. Right? So hash set makes no guarantees to the iteration order of the set. Right? In particular, it does not guarantee that the order will remain constant over time. Right? So if you have a set and you loop over it, and then you loop over it again, you might get a different sequence of elements coming back out. Right? Now your other choice is tree set. Okay? So tree set also has fast add, remove, and contains. Right? But it's slower than hash set, which is why you normally choose hash set. Right? So for tree set, these operations have log n complexity. Right? So still very fast, but they're not constant time. And in general, a hash set will beat a tree set in terms of performance every time. Now, the nice thing about tree set, though, is that it maintains the elements in sorted order, right? But that also means the elements have to be sortable, right? So in other words, you can't make a tree set of elements where you can't sort the elements, right? In Java, you have to implement what's called the comparable interface, right? But we'll get to that a little later. There is a third kind of set that is occasionally useful, right? So notice the big difference between these. Well, there's two big differences between these two sets, right? So hash set has O1 complexity for its most frequently used operations. Tree set's O log n for the same operations, right? So a little slower. But tree set guarantees some kind of iteration order, right? So in this case, it guarantees sorted iteration order. Right? A linked hash set is like a hash set, so it has very fast add, remove, contains. Right? Again, O1 in terms of their expected complexity. It's slightly slower than hash set, right? So very slightly slower than hash set because there's some extra overhead needed. The reason it needs the overhead is because linked hash set will give you the iteration order for a linked hash set is the same in which you put things into the set, right? So if you put in A, then B, then C, when you iterate over the elements, you get back A, then B, then C, right? So the iteration order is guaranteed to be identical to the order in which the elements were added to the set. Right? The reason why you don't normally use linked hash set is because it costs more memory than hash set. Right? The additional cost of memory is proportional to the number of elements in the set. Right? So if you have a set of 1 million elements, right, you need an extra 1 million units of memory compared to hash set. All right, so you've got 3 choices, but really, for the most part, you have 2. Okay? Now, you can't do much with a set. That's the interesting thing, right? So a set's not like a list where you can ask for a random element in the list, right? Or loop over the elements and do things with them, right? Sorry, you can loop over. So all you can do with a set is basically loop over the elements of the set, right? So if you want to loop over the elements of a set, you use a for each loop, right? There's no indexing, right? So you can't use the regular loop, it's not natural to use the regular loop that counts. Right? So you use a for each loop. Right? So if T is a set of strings, then you loop over the elements by saying for each string S in T, right? Where the colon means in Java, at least for the loop, right? At least for the for each loop. Okay, now why would you want to use a set, right? So here's an example of when you'd want to use a set. So you have a list, and you want to find all of the elements that occur 1 or more times. Right? So in other words, I want to find the duplicate elements in the set, right? Or in this case, I want to remove them. Right? So imagine, so this is an example where I have an account. I have a list of student account numbers. Right? So array list string, CS account, that's just a list of student account names. Right? So it's your net ID names. So for example, if I have the course membership list, right, that I can pull off of OnQ, I can get back your net IDs from that list, right? If I want to check if you're only in the list once, and there's no guarantee that you're only in the list once, right? Hopefully you are only in the list once, but if I want to check, I can take that list, right, and give it to a set, right? So create a set using the list by calling the constructor, right? And that thing unique counts will now be a set where only every net ID appears once in the set. Right? And so in other words, it removes all the duplicates from that list there. It doesn't remove them from the list. Sorry, it gives you back a set that contains the unique items in that list. Right? And if I want to sort them, I just use a tree set instead. Right? So here I use a hash set. Remember, hash set, there's no guaranteed ordering of the elements. But if I use a tree set, I now get your net IDs in sorted order. Right? And I use a linked hash set if I want to maintain the same ordering as the elements in the input list. Right? So when I get your student account IDs from OnQ, right, normally it'll give them back to me in the order where in alphabetic order of your last name. Right? If I want to keep that ordering, then I create a linked hash set instead. Right? And I'll get a unique set of student account names where the order is the same as the original list. Right? It's just that the duplicate elements have been removed. Okay, now if I want to find the duplicated elements, so instead of removing them, I want to find what they are, then you use toSets. Right? So I do the same thing. Right? So I'm going to do something similar. Right? I'm going to have the set of unique accounts, and then I'm going to have a set of the duplicated accounts. Right? I'm going to loop over that list. Right? So for each string account in CS accounts, right? I'm going to check, is that account name already in the set unique accounts? Right? So if unique account dot add account, not. Right? So in other words, if I can add that account to the unique accounts, if I cannot add that account, sorry, if I cannot add that account to that set, right, then I know that you're a duplicate, that's a duplicated account name. Right? So add returns true if account is not in unique accounts. Right? So if it returns false, I know that's a duplicated account, so now I can just add that account to the duplicated account list, set. Right? And that gives you both sets. Right? That gives you the unique account set here, because I'm adding that, the account to the unique accounts. And it also gives you the duplicated accounts, right? Because you're adding the duplicated accounts into the second set. Okay, this is a picture of what's happening here, right? So unique account, that's a set. Duplicated account, that's the second set. There's my list of student names, or student account names, right? These are not Queen's student account names. These are from a different university, right? So what I'm going to do is I'm going to loop over this list, right? And I'm going to try to add them to unique account. Right? So the first element of the list is not in unique accounts, so we add it to unique accounts. Right? Second element, not in unique accounts, so it gets added to the first set. Third, right, not in unique accounts, so it gets added here. Fourth, right, and now when I get to the fifth one, right, that account name is already here. Right? So add returns false, which means it ends up getting added into the duplicated account list set, right? And then the same thing here, right? That name appears in the set of unique accounts, so now I add it to the set of duplicated accounts, right? And now you've got the set of unique account names and the set of duplicated account names. Okay, so the set union is the same as the mathematical set union. Right? Suppose I have a set containing the accounts of students who completed assignment 1. Right? And then I have a second set of students, a second set containing the accounts of students who have completed assignment 2. Right? I want to know who's completed both assignment 1 and assignment 2. Or sorry, either. Right? I want to know who's completed either assignment 1 or assignment 2. Right? And for that, you compute what's called the union of the two sets, right? So I try to join the two sets, the contents of the two sets. Right? S1, add all S2, transforms S1 into the union of S1 and S2, right? So in other words, I'm going to try to take all the elements from S2 and add them to the set S1, right? And that will give me, if you think about that for a second, right, that will give you the set of all students who've completed either assignment 1 or assignment 2. Right? So you make a set called either assignment, right? You initialize it with the contents of S1, right? So that's all the students who have completed assignment 1. Right? Now you try to add all the students who have completed assignment 2. Right? So here's S1, right? That's assignment 1. Here's the list of the list or the set of students who have completed assignment 2. Right? So I start out with the third set copying the first set. Right? So this is equal to the set of students who have completed assignment 1. Right? These two are the same now. Right? And now all I do is I loop over these elements and try to add them to the third set. Right? So when you loop over this set, right, the first person here, SP Kuma, well, they're already here, so we don't add them again. Right? D Parrot is already here, so we don't add them again. Huxley is not in this set, so we add them there. right? And DevC is not in the original set, so we add them there, right? And so now you've got the set of students who have done either of the two assignments. Okay, so the intersection is when you want to find out who have done both, right? So if I have, again, a set of students who have completed assignment 1, the set of students who have completed assignment 2, I want to know who's done who's done both assignments, right? Then you want to compute the set intersection. Right? So retain all is the method that transforms the set S1 into the intersection of S1 and S2. Right? So retain all will try to keep all the elements of S1 that are also in S2. Right? And it will remove the elements that are not in S2. Right? So again, S1, that's the set of accounts who completed assignment 1. Right? S2, that's the set of accounts who completed assignment 2. Right? So if I want to know who's completed both assignments, right? You make a set equal to S1, right? And then call retain all with S2. Right? In other words, keep all the elements in both assignments that are also in S2. Right? So there's the set of students who have completed assignment 1. There's the set of students who have completed assignment 2. Right? I start out with the both assignment set by copying the first set. Right? Now I'm just going to loop over this set, right? And keep the elements from this set that are also in this set. Right? So you're looking for the common elements in the two sets, right? So SB Kuma appears in both sets, and D parrot appears in both sets. So that's the set of students who have completed both assignments. Right? And if you look here, right, those are the students who have only completed one assignment. Right? Okay, now if I have a set containing, so again, same thing, right? Two sets, one of the students who have completed assignment 1, a second students who have completed assignment 2. If I want to find the set of students who've only completed assignment 1, right, I want the set difference. Right? So S1 remove all S2, right? We'll remove all the elements from S2 that are also, so we'll remove all the elements from S1 that are also in S2, right? So that transforms S1 into the set difference of S1 and S2, right? You do the same thing again, right? You just make a new set and you copy the first set, right? And then you remove everything that's also in the second set, right? That's what remove all does, right? So again, I copy the first set, right? And then I'm going to remove everything that appears in here. Right? So SB Kuma appears in both sets, so I remove SB Kuma from this set. Right? D parrot appears in this set, so I remove D parrot from the third set. Huxley does not appear here, so I don't do anything. Right? DevC does not appear here, so I don't do anything. Right? And you're left with this students HP 1304 and Area 98. Right? As the students who only completed assignment 1. Right? Now, if you want the students who only completed assignment 2, right, you start by copying set 2. Right? So this set here would be the same as this set here, and then you would say only assignment 1 dot remove all S1. Right? So remove all the students who did S1. Okay. 11:05. I'm going to move on to the. Oh wait, I would move on to the next next lecture, but it's not up on OnQ. And okay, so if my computer reboots, I'll start the next lecture. The problem is it's going to want to install a bunch of updates, and that's probably going to take a while. Yeah, that's not good. Oh, it's a big update. It's not a little update. It's a big one. Okay, so I'm going to not start a lecture 10 here, and I will end the class here. If you didn't get my email last night, labs have been moved permanently online, so there's no in-person labs. Jeffrey Lab is not very pleasant to be in. And I'm almost 100% sure you would rather work on your own computers than the Jeffrey Lab computers. They're not nice. It's not a nice lab to be in. So we're going to go permanently online. The link for the Teams meeting is already up. Right? You should have received that already. Okay? Thank you, everybody. Sorry about the computer problems.